Hello everyone, welcome to my your programming club. Today we will be solving another daily LeetCode problem, and the problem's name is Stone Game Part 2. So the problem statement goes like this. There are two players, Alice and Bob, continue their games with the piles of stones. There are a number of piles arranged in a row, and each pile has a positive integer number of stones. Okay, and the objective of the game is to end the game with the most number of the stones for each of the players. Okay, and Alice and Bob takes turns one by one, and Alice will be starting first. Okay, and initially M will be set to 1. So the problem statement further explains what this M is. On each player's turn, that players can take all the stones in the first X remaining piles. Okay, so if let's say X is 2, then the player can take all the two of the all the two piles, or he can take a single pile. Okay, it's totally dependent on him. Okay, so o- player can take all the stones in the first X remaining piles. Okay, and X will be ranging from 1 to twice of this M. Okay, so if M was initially 1 and then twice of M will be 2, so X can be ranging from 1 to 2. So either the player can take a single pile or double pile. Okay, so it cannot be lesser than 1 and cannot be greater than twice of M. Okay, and then what will happen once the stones are taken from the number of piles which lies within this range, then we will set our M's value to the maximum of M's current value, and the piles number of piles that of stones which the player currently took. Okay, so your M's value will be updated. Okay, and the game continues until all the stones have been taken. Okay, so basically you have to take all the piles of the stones. Okay, so once we are finished with all of them, then we will end the game. And assuming that both Alice and Bob plays the game optimally, so both try to win the game, you have to return the maximum number of stones that Alice can get. Okay, in the game, so you have to return a situation, number of stones in a situation where Alice is getting maximum number of stones. Okay, so before thinking of an approach, let's have a quick look at the constraints also. So according to the constraints, the length of the piles array will be of order 100, and each entry in this array is ranging from 1 to 10 raised to power 4. Okay, so now let's see how we can solve this particular problem. So if you want to try out all the possible combinations, so a very straightforward approach that might be coming to your mind is a brute force approach, and try out all possible ways. Okay, so for that what you have to do is, so X was ranging from 1 to twice of M. Okay, and you know that maximum number of choices you can use at a particular given instance is 2 into M. Okay, so at every instance or every step you will be having 2 into M choices. So 2 into M into 2 into M into 2 into M, and this thing will continue. Okay, and it will continue the number of, let's say the size of the pile is n piles array. Okay, so if there are n such instances where you have to make the decisions of how many number of piles you have to take of stones, then there will be order of m 2 into m whole raised to power n. number of choices. Okay, and m is also constricted in a way because this m cannot be larger than the number of piles available. So a close approximation to this can be order of 2 raised to power n. Okay, and you can see that it's exponential, and the n is here 100. So 2 raised to power 100, order of 2 raised to power 100 will be greater than the operations limit which is there. Basically, the number of operations required by your program to solve a particular problem should be less than these number of operations. So 10 raised to power 8 operation limit is there. Okay, ops limit you can say. So you will exceeding that. That's why your solution will not be getting accepted, and you will not be getting a accepted solution, and you will be getting a TLE, time limit exceeded. Okay, so in order to get our solution accepted, we need to optimize this brute force approach. Okay, so optimization required. Okay, so for what kind of optimization technique will be suitable for this? For we have to make couple of observations in this problem, and those observations are, the very first observation is, let's say there are some piles of stones. Okay, this is your piles array. Okay, let's change the color here. Okay, these are the number of the stone piles that you are having. So firstly there are a stones, a number of stones, b number of stones, c number of stones, d number of stones. Okay, so let's say we were mentioned that Alice was starting first. Okay, what if Alice took the first stone? Okay, so then Bob will say that okay, I will take the next stone. Okay, this will be taken by the second person, which is Bob. Okay, now the sub problems remains that these two piles are gone. Okay, and a part of the problem is remaining, and that part is C and D. Okay, so this is one situation. Okay, let's consider another situation. So this can you can consider as combination 1 or scenario 1. Let's consider another combination 2. Okay, so the piles array is same, but the set of choices will differ this time. Okay, so here this time what Alice will do is, Alice will pick two of the stones. Okay, so two of the stones are picked by Alice. Now Bob have to make the decision, but the sub problem that was occurring earlier, C and D, is now again occurring. Okay, C and D is again required to be solved. Okay, so essentially this sub problem is being repeated. Whether whichever of the persons have to make the decision of choosing them, but you can see there is a overlap of sub problems. Okay, so this overlap causes extra work to be done for computations of same sub problem again and again. Okay, extra work required for recalculations. Okay, so in order to avoid this extra work, we could have just memorized this somewhere, and whenever we see a sub problem being repeated, we could have just returned it from there instead of doing the calculations and again and again. So this need to be avoided. Okay, so this particular property of overlapping subproblems, uh, part of problems is as the name suggests, is called overlapping subproblems property. Okay, so if you are new to this particular kind of property of a problem, I will provide a link of an article explaining this in detail, so you can definitely check this out in the description section. The link will be provided there. This was observation 1. Now let's consider another observation. So observation 2, since we have to return that maximum number of stones Alice can achieve, so what we have to do is Alice can achieve maximum number of stones if at a particular instance, if Alice knows if she makes a particular choice, then how many stones she could have in future. Okay, then how many stones she could have in future. Considering Bob also plays optimally. Okay, okay. So she need to consider that. So if she knows, then she will be definitely picking the right choice. It's like a person is standing in front of three doors. Okay, one, two, and three. Okay, and there are some tunnels behind these doors. And if the person is able to know how much treasure is and he is allowed to choose only one of the doors, how much treasure is there in these doors, then he will be picking the right choices, or there might be some dangers out there. So he need not to pick those doors if he already knew which is the door which is having the treasure that he or she wants. Okay, so it's a similar kind of situation. Okay, so if Alice knows beforehand what her present choice would lead to, what future outcomes, then she will make the most optimal choice right now. So in a way we can say that by solving and by knowing uh, future outcomes, and by solving the current the problem optimally, we will be able to solve the whole problem in an optimal way. Okay, by solving current sub problem optimally, we will be able to solve the whole problem optimally. Okay, solve the bigger problem or the whole problem optimally. So this kind of property in which the solution of smaller subproblems can be combined and made into the solution of bigger subproblem is called optimal substructure. So you can consider this as smaller subproblem, solution 1, okay, and then solution 2, and then solution 3. So these are subproblems and we can combine their results and we can simply form the solution of the bigger problem. Okay, this is a property and the property's name is optimal substructure. Okay, so if a particular problem statement is satisfying these two properties, then a optimization technique dynamic programming can be applied here. So if you are hearing this term for the very first time, then I will be also providing link of this particular one in the description section. You can check the articles link on dynamic programming, and link of this particular optimal substructure property will also be provided in the description section. Okay, so you should definitely check them out. What dynamic programming does is, as we already talked about, that we need to store our results in order to avoid extra work. This is one part of dynamic programming, that storing the sub problem results. Okay, the program results in order to avoid extra work. Okay, and then what it does is it use these subproblem results to build the solution of bigger problems. Okay, so use these subproblem results to build the solution of bigger problem, or you can say sub problem. Okay, and in this way you will be having the solution of the whole problem by breaking it into small sub problems and then solving them those sub problems optimally. And on top of that we are storing the results of each of the sub problems, so that if there is again an occurrence of a sub problem, then we need not to do any recalculations for that, and we can just return from the results that we have memorized. Okay, this way it will optimize the brute force approach. So in a way it is just optimization over brute force. Okay, so now considering that you have familiarized yourself with dynamic programming and those two properties, now let's see how we have implemented this in our solution, our problem, to be specific. Okay, and for that what we will be doing is, and let me for that part, and in order to avoid the problem videos to be made any further longer, let me take the code to the board and I will be explaining the approach and the code in one go, so it will save some time, as we must have already taken a large chunk of time in explaining what dynamic programming is and how and when optimization is required. So let me remove this toolbar. So what we will be doing here is, so consider that Alice is at a particular instance. Okay, and she have to make some choice. Okay, and what will determine the current state of Alice, or current state of decision making at which she is? The current state will be determined by two things. The first thing will be the starting index, or the, let's say there were four of the piles and of stones, and two have already been gone. Two went to the players Alice or Bob, and Alice is right now have to make decisions for this much portion. This is remaining right now. Okay, C and D is remaining, and rest of the things are gone. So the very first thing will be the index, starting index of the pile, from where the pile is now starting, and rest of the piles were consumed by the players while making the choices. Okay, this will be the first factor that will be determining it, the state of the choice making or the decision making at which Alice is at. The second factor that we will be determining is that what is the current value of M. Okay, current value of M. Okay, so that will determine how many stones he can take, and depending upon the range will be decided. So the range is nothing but the X is the number of stones Alice can take. Alice can take. So it will be ranging from 1 to twice of M. Okay, so that's why these two factors will be determining the current state of decision making. Okay, so this will be determining current state. So as there are two variables that determine the current state, and these are called state variables, by the way. So that's why a 2D dynamic programming structure will be required in order to store your results of the sub problems or the intermediate states that you will be encountering while solving or trying to solve the bigger sub problem. Okay, so that's why a 2D DP will be required, or dynamic programming structure, and we have called this as the state matrix. Okay, and this represents how many stones Alice can take if she is a particular index and having a particular value of M with her. Okay, so this is what the state matrix here represents. Okay, and then what we will be doing is, since we were talking about that we need to know what kind of choices Alice will be having, like these doors will be there and Alice is standing in front of them. So she need to know what out if she decides this one, will there be treasure or not. Okay, in a way, how many stones she can collect. So she will greedily pick the best outcome. Okay, in order to do so, what we are doing here is we are taking the maximum suffix values of the piles of the stones. Okay, so suffix values are for that because if you are at a certain point and you know how many number of stones are lying ahead, then it will be a way that you are knowing the future. So that's why we are using a suffix sum. So that's why we are calculating suffix sum here, suffix sum of piles of stone. Okay, so this is just a standard suffix sum implementation. If you are you know not able to make sense of it, then you can ask them in the comment section. It is pretty simple. If it is the very last entry, then you will just be having the piles array. Let's say the array is like this, 1 2 3 and 4. Okay, if you are at this one, then your suffix entry will be having only 4. Next time you will add 3 and 4, so this time it will be 7. Next time you will have 2 and 7, so this time this will be 9, and then 1 and 9 will be added. This time it will be 10. So 10 9 7 4, so it will be like this. Okay, so I hope you are able to make sense how this suffix array is being calculated. Okay, and yeah, so once the suffix array is calculated, it will be used to form the results of this state matrix. Okay, and how we will be using that is, firstly we will consider the situation that Alice is at a certain instance where the m value is that much large that she can take all the remaining stone piles. Okay, so in that case he will take all the remaining stone piles, which will be nothing but suffix pile sum at that particular index. Okay, so if Alice is here and she want to take all the remaining stones, like these stones, so she will know that okay, 9 stones are only remaining at this particular point, because 2 plus 3 5 and plus 4 which and it will be 9. So suffix sum will help us in this kind of situation. Okay, so this is one situation, and then you will build your solutions from the uh, considering the future outcomes. Okay, so you will, since we have to consider the future outcomes, so we should be building it in a reverse way. So if the piles array is given like this, so you should be building your solution in this way. So that's why we are starting from the end. Okay, because if you are at the end, then you will not be having any future outcome. So if the piles array is 1 2 3 4 and you are starting at 4, there is no future before this, after this. Okay, and if you are at 3, then there is one future determining thing, which is 4. So that's why we are starting from the end. Okay, and then we are building our solution. Then what we are doing here is, then we are setting our m value. So since I already told you, your m value can only be varying from 0 to n, where n is the size of the given piles array. Okay, so you will vary your m value from 1 to n, or you can say size. So then according to your m value, your x value will be determined. Okay, so x was having this range of 1 to twice of m. Okay, so this is what we are doing here in the third nested loop. Okay, and it should not exceed the number of piles that we are having. Okay, if you are taking some amount of piles, that it should not exceeding whatever is left. Okay, so that's why this condition, and this is the range of x value. Okay, and then we Alice need to know that what future collection she can have if she makes a particular choice. Okay, so this is what future collection is having. it is nothing but, let's say there are 9 stones left. Okay, and if Bob plays optimally, then let's say Bob consumes 4 of them. Okay, 4 of them are taken by Bob. So how many stones will be left in future for Alice? So it will be 9 minus 4, which will be equal to 5. So this is what we are doing here. Suffix sum is the current number of stones that we are having, and then we will simply subtract those if Bob plays optimally. Okay, and since it was mentioned that m's value will be updated at each decision from the maximum current m's value and the current stones that were decided to be taken. Okay, so once Alice knows the future collection, then she will update her state. Okay, her present state knowing the best future outcomes. Okay, and then where will be the answer be stored? It will be stored when m's value was initially 1 and Alice have to make the decision when the index value was 0. So all of the stones were present. So that will be our answer, and you will be simply returning it. Okay, this will be the approach and implementation of the whole logic. And if we want to have a discussion on complexities also, time complexity wise, this will be order of n square, n cube, because we are using 3 nested loops and they can be of order n. Okay, so that's why order of n cube. And space complexity wise, since we were using a 2D array, each of size n, where n is the size of the piles array. Okay, then the space complexity will be order of n square. So these will be the complexities. So I hope everything is clear to you. If you are still having any kind of doubts or any queries in general, then you may ask them in the comment section. And I really hope this solution walkthrough added some value to your journey of honing your DSA skills. Until next time, keep solving more and more problems, and I will be seeing you in the next video. Thank you for watching.